Okay. Again, some announcements. The final of the course is on 16th of December, and it's in this classroom. The registrar has allocated 9 a.m. to 12. I probably won't have a 3-hour exam. It'll most probably be 2 hours. So the allotted time is 9 to 11, 9 to 12. It's Thursday, so I think 2 weeks from now. And there's a lab next week. You must have received the announcement. Sign up for the lab. You shouldn't view the lab as some sort of a test. It's more for you to get some experience configuring routers or configuring end hosts, and also to look at some routing protocols. And the lab is about, it shouldn't take more than 2 hours, and you'll be doing it in groups of four. The last lecture next week will be a review session before the final. Before that, is there anything that you'd like me to cover in the remaining time? I'm planning to do wireless networks, which we'll definitely do. And in today's lecture, maybe we'll cover MPLS. But if there's something related to networking that you wanted to know, yeah. Voice over IP. The whole protocol? Okay, I can maybe get into how SIP works. We'll take a look at that next lecture, maybe before the review session. Anything else? No, Thursday is the last Thursday. But we could go through a review or cover something that you're interested in. Any requests? We can think about it. Maybe next lecture. So last lecture, we were looking at the differences between hubs and switches, and we saw that switches are link layer devices. They are much more intelligent than hubs. So they are preferred in terms of performance, but because they are much more intelligent, they are also more expensive than hubs. Another thing that we didn't mention was well, we spoke briefly last lecture that switches are plug and play and self-learning. So they learn the interfaces on which particular nodes lie with the corresponding MAC addresses. So the switch table that a switch builds, it's self-learning. You don't have to configure anything. Unlike a router where you have to run some sort of active routing protocol where you have to exchange messages and come up with a routing table, the switch is self-learning. It learns this switch table by looking at the link layer frames that are passing by, and then by looking at the MAC address and the interface on which it receives a frame from the source address, it can compute or it can construct this switch table, which then lets the switch selectively forward these frames to the right interfaces. There is, however, a sort of a caveat here. Switches switches or bridges. Have you heard of bridges? Bridges are switch-like devices, and they were sort of the precursor of switches. And bridges could lead to what are called broadcast storms or route loops. So here we say that the switch has the switch table. Depending on the switch table, it will route packets or route frames, link layer frames, to the appropriate interface. Now nothing here in the switch table, you can think of this switch table as kind of a routing table. Nothing here prevents routing loops or switching loops to occur if you have an interconnection of switches. The way we saw routing loops could occur with routing mechanisms when we saw different kinds of routing algorithms. Loops can occur with switches. So to prevent these loops, switches also implement a spanning tree algorithm. So where the whole network is converted into a spanning tree and frames are forwarded only along spanning trees to prevent switching loops. So that sort of adds to the complexity of switches beyond hubs. So we saw what filtering and forwarding means in the context of a switch versus a hub. So what switches can do is they can provide traffic isolation in a network. So if you had a large interconnection of smaller networks and you connected these smaller networks with a hub instead of a switch, then all of these networks form one collision domain. By having a switch connect these networks, you're isolating these separate subnetworks, and the collision domain is restricted to these subnetworks. That improves the performance of these networks. Now you could also do this thing with a router instead of a switch. So why not use a router instead of a switch to connect these networks? Yeah. It's more expensive. Is there any benefit of a router? It's more expensive. For a router, you have to configure it. Switch is self-learning. The one advantage a router has over a switch is that the router doesn't have to run any kind of spanning tree algorithm. Routing loops are avoided by the routing mechanism. So that's the one advantage of using a router instead of a switch. So here's a comparison between hubs, routers and switches in terms of interconnecting different networks. Hubs provide no isolation, but hubs are plug and play. You don't have to configure anything. Cut through, let's ignore the cut through part. It's a very simple concept where you can start forwarding a packet before receiving the entire packet. So you don't really store and forward. That's the idea of cut through switching. With routers, you have to store and forward. The one advantage that routers have over switches and hubs is you can do optimal routing. And you don't have to worry about loops or run spanning tree algorithms. So you can do more intelligent things with routers than switches. But that's the only advantage you might have with routers over switches. The other advantage is that routers scale up to a lot more nodes. If you have thousands of machines on your different networks that you're trying to interconnect, then it's much better to use routers instead of switches. Why is that? You have a device, you have different networks connected through a device. Okay. If you have thousands of machines on these different networks, it might be advantageous to use a router instead of a switch. Think of how a router routes versus how a switch routes. So what is a switch route based on? No, not very centralized algorithm. So how does a switch route frames or link the packets? Yeah, it does a table lookup. So even a router does a table lookup. Yeah. Sorry? Yeah, the difference is because a switch uses a MAC address to switch or route. Router uses an IP address to route. So with a MAC address, what you have is a flat address space. Any two MAC addresses can occur in any part of the network. So this switch will have to maintain a switching table that contains all of those MAC addresses. So it might have thousands of entries in these MAC addresses. Whereas if you use a router, the IP address is more hierarchical. So you can aggregate addresses of subnetworks. So you can route based on prefixes. So routers will scale better to larger networks than switches. So routers scale better. That's another advantage. For smaller networks, switches are fine, but for larger networks, because of the address space, the MAC address space versus the IP address space, routers might be better. We're going to skip PPP. It's another link layer technology used for dial-up lines. There's nothing sort of technically difficult to understand, and it's not sort of a hot technology. So we're going to skip PPP. We'll look at you've heard the term MPLS, multi-protocol label switching. That's sort of a very hot emerging technology. If you go out and get a networking job, I'm sure you'll encounter the term MPLS all the time. So MPLS, we'll look at what MPLS is, and MPLS uses ideas of circuit switching. So before getting on to MPLS, let's look at this concept of virtualization of networks. So in virtualization of resources, what you do is you abstract out a certain resource, and then you don't worry about the details of that resource, only the services that you get from that resource. How that resource is implemented is not your concern. So for example, you have Java virtual machines or virtual memory based operating systems. Operating system just expects some amount of memory. How that memory is arranged in terms of cache hierarchies or page or disk memory, that's not the concern of the operating system. It has performance issues, but it will still get access to that memory. Similarly, how a Java virtual machine is implemented in a particular CPU architecture, that doesn't concern the Java programmer. The Java programmer will get access to all the services it expects from the Java virtual machine, and then it can function. So the internet was really an effort to virtualize networks. So earlier you have many different kinds of networks, and what the internet provided was a way to virtualize these networks and interconnect all of them. So what it provided was a layer, and we have seen aspects of it earlier. This layer enabled a gateway to be placed, which would let data flow between a particular kind of network, let's say the blue network, and a different kind of a network, the pink network. So this network is operating, let's say, completely differently using satellite technology. This network is operating on physical cables. But this gateway let these two networks talk to each other. And this gateway is what evolved to be the IP layer or the network layer. So now with the internet layer, whatever was below this layer is not of any concern to the IP layer. Everything on the IP layer is a single uniform identity. So below the IP layer you can have all sorts of heterogeneity, and at the IP layer everything becomes glued together into one entity. And above the IP layer, all of these devices or machines or applications can talk to each other. So now remember where we came across the link layer. Where is the link layer set? The link layer sits below the network layer or below the IP layer. So below the IP layer we have many different kinds of network technologies which are hidden from the IP layer. Once you're at the IP layer, you don't really care how the packets have come, whether they have come from cable modem, satellite connection, dial-up links using PPP. And what's interesting is that there are other technologies which are themselves networking technologies like ATM and MPLS. They can also serve as a link layer. So what you have is that below the network layer, the link itself may not be a physical link. You can have a virtual link, and that virtual link might be connected using a whole network. So as an example, these ATM, MPLS, they are separate networks, and what we saw earlier was tunnels. When you have tunnels connecting to IPv6 routers, the tunnel was going through a number of different IPv4 routers. But in the IPv6 world, there was a single virtual link between the two IPv6 routers. So the tunnel was acting like, let's say, kind of a link layer technology. So even though we have studied link layers as something which connects to physical links to each other, link layer might be more broader than that. It might refer to a virtual link and not a physical link. And the virtual link itself might be a network. So the virtual link could be a tunnel which is going through many different routers. It could be an ATM cloud. It could be MPLS and things like that. So ATM was technology which was developed in the mid and early 1990s. It was supposed to be a standard for high-speed networks, and it was developed by telephone companies. The telephone companies were the driving force behind this technology of ATM, and because telephone companies were behind it, they tried to implement the technology that they were familiar with and comfortable with, and that was circuit switching. Internet used packet switching, but ATMs used a form of packet switching using virtual circuits. And virtual circuits gave you much better performance. So the ATM switches of early 1990s operated at much higher speeds than, let's say, what the routers, which were doing routing based on packet switching, were capable of. So IP routers were not as fast as ATM switches. But slowly IP routers caught up. And now what has happened today, ATM could never sort of penetrate to the end host. This technology was supposed to go to end systems. Your desktops and your laptops were supposed to run ATMs, but that never happened. At the end systems, IP won. But ATM has not disappeared. So ATM today is still used, and it's used as a link layer technology. So it was supposed to be a complete networking solution, but these days it's used only as a link layer technology. So it connects, ATM connects to routers, but that connection might be going through a complete network. But the link layer technology that is used is ATM. So it's like a virtual link, but ATM is hiding that virtual link from the network layer. So this just shows an example of this. You have an IP network. You have an ATM network, which consists of many different ATM switches, and you can think of that as a cloud. These ATM switches are able to connect different IP layer devices to each other. Now from the view of IP, all of these are directly connected to each other, as if they are part of a same physical link. You can maybe think of this as a wireless network or a LAN, but it's being operated underneath. It's very complex. ATMs are working, but as far as the internet layer is concerned, they have a direct connection to each other. And ATM provides a mechanism of directly transmitting frames or packets between these devices. So ATM sort of could never make it above the network layer or to the network layer, but some ideas of ATMs have survived. And the idea that has survived is this idea of using virtual circuits. So I'm going to skip all of this, and I'll come to MPLS. So MPLS is an idea that has taken off, and it's being used widely in today's IP networks. So what does MPLS stand for? MPLS is multi-protocol label switching. The initial goal of MPLS was to use the idea of virtual circuits, which were present in ATMs, and implement them on the internet so that you could have faster routing, faster switching. So how does MPLS work? Well, you have your packet with the IP header. To the IP header, you add a fixed length MPLS header. There is a fixed length MPLS header added, and after the MPLS header, you might have other link layer headers, PPP or Ethernet or whatever have you, even ATM. All the routing or switching on IP routers, which are MPLS capable now, will be done based on this MPLS header. The IP header is not looked at all. So you have routers on the internet they'll get these packets and they'll perform routing based on this header. They're not going to look at the destination address. And that speeds up routing or switching a lot. So why is that? You don't have to look up the tables. You still have to look up this MPLS base table. But now you have a fixed length header and a fixed length label. That lets you switch very fast. So take an example. Let's say you have an autonomous system which is connected to only 2 other autonomous systems. Okay? Now, any packet that is entering this autonomous system has only 2 possibilities of exiting this autonomous system. It can either go to 3 or 2. Okay? So now if a packet enters, finally it's only going to exit in 2 locations. Do we really have to look up all the possible autonomous systems to make a routing decision? Not really. You can, based on the first packet, if you figure out where it's going, then for all the next subsequent packets, you can maybe follow the same path within the autonomous system. To reach a particular destination autonomous system. Moreover, suppose you have a number of different possible paths to this egress point. So you have, let's say, an entry router and you have 2 different paths that take you to this exit point. If you're doing routing based on the net on IP, on the IP destination header, how do you route packets? How will this router route packets? It will look at the destination IP address, it will consult its routing table, and then it will forward the packet along, let's say, 1 path. With IP routing, you do destination based routing. Given a destination, you'll choose an interface and send the packet along that path. So what that means is that the other alternate path that you had is going completely unused. How do you use this path? Another example could be, suppose this is an ISP and it has 2 different kinds of customers. Customer A is paying more than customer B. So customer A's packets arrive, customer B's packets arrive. Both are trying to go to the same autonomous system. Okay? Now, at the router, with IP routing, with destination based routing, Your routing is going to look the same for customer A versus customer B. You'll route them both along the same path. Now, if you have the ability to also use the source somehow, then you might want to send A on a path which is less loaded, or which is a shorter path which gives less delay, or maybe it's encrypted. It provides more security. So people wanted to enhance IP routing in some ways, but also retain the simplicity of IP. And MPLS used ideas from virtual circuit technologies to come up with all these enhancements. So MPLS not only lets you do some neat things, it also lets you do these things faster than IP. So we look at how MPLS is able to do all that by looking at what an MPLS header looks like. So MPLS capable routers, they are also called label switch routers. They are going to forward packets to the outgoing interface based only on the label value. So if you saw the header, in the header there is a label. What the routers do is they simply look at the label and then they forward the packet based on the label. They will not look at the IP header at all. So this is ignored. So this MPLS forwarding table is separate from the IP forwarding table, and normally it's much smaller than the IP forwarding table. The IP forwarding table, that data structure could be huge, but the MPLS forwarding table looks very small. We'll look at examples of what these forwarding tables look like. To create these forwarding tables, you need a different signaling protocol. And there's a signaling protocol that has been developed which is separate from routing protocols. It's called RSVP. RSVP stands for Resource Reservation Protocol. RSVP TE. TE is traffic engineering. So it's resource reservation for traffic engineering. MPLS must coexist with IP-only routers. So MPLS sort of provides a tunnel between IP-only routers. Let's look at an example here. So in this example, the blue routers are routers which are capable of MPLS. The white routers are IP-only routers. So the white routers are not going to have any MPLS forwarding table. They'll only have the IP routing table, and they'll route based on the IP routing mechanism. The MPLS forwarding table, on the other hand, looks something like this. It has 4 entries: in label, out label, destination. So the routing in IP, the routing table in IP only had the last 2 entries. You had a destination prefix and you had an outgoing interface. In the MPLS forwarding table, you have in label, out label besides destination. So the labels refer to the virtual circuits that have been set up in this MPLS network. So take an example of this router here. The packets that arrive at this router, since they are coming from an IP only router, not an MPLS router, they won't have any in label. So this router is sort of standing at the edge of the MPLS network. It will look at the destination for the packets, and based on the destination, it will not only choose the outgoing interface, but it also chooses the outgoing label. So it looks at the packet, it looks at the destination, it will choose the appropriate outgoing interface, and then it chooses, and then it places a label in that packet. So that label is overwritten here, this field. Every MPLS capable router will first look at the label, and then when it's forwarding the packet, it will override this label based on its table. So now look at these two routers. Yeah. Could be anything. It's 20 bits you can use. It's just an example. No, no. It's not part of the links. But what these labels do is they create a whole virtual circuit between the ends of this MPLS network. So the outgoing label here for destination A is 10. The outgoing label for destination D is 12. Okay. At this router will look at the incoming label, and based on the incoming label, it can quickly decide which interface to use. 10 indicates that it's going to A, and the outgoing interface that has to be used is 1. 12 indicates that it's going to D, the outgoing interface is 0, and it can replace the outgoing label. Why do you replace the outgoing label? It allows more flexibility for these routers. So now look at the look at router 4. For the same destination A, it has two different outgoing labels, 8 and 10. Right? Why would you have a scenario like this? Well, what we spoke about earlier. You could use it for load balancing. So you'll send part of the traffic that is destined for A along this route, part of the traffic that is destined for A along this route. You could also use it for service differentiation. Let's say the more important traffic goes along this route, which has more capacity, lower delay. Less important traffic could go along this route. So the question is, where is this labeling done, the out labeling? So what the book doesn't talk about and what's not in the figure is that there is a router at the edge of the MPLS network called an LER, a label edge router, which will do all this labeling. So a label edge router, you can think of that as overlaid right here, does this outgoing label, does the initial label. And from there subsequently, these routers can override the outgoing label. Yeah. So each router will have their own labels. The only requirement is that they convey these labels to their neighbors, to the links that, on the links that they are connected to other routers, they are going to convey these labels using Wrttp TE. The advantage is that this router here, it need not know about the labels that have been set by this router here. It only needs to know about the labels that have been set by this particular router here. So you don't need some sort of centralized information. You share information only with your neighbors. So this router here only knows about the incoming label 6. It has no knowledge about incoming label 8. So that allows easier management of these MPLS routers in a distributed manner. So how can you implement a virtual private network using MPLS? Well, the label edge router sitting here could look at the source address, which is the source address of a customer of a virtual private network, assign a completely different outgoing label to those packets and send them along a different path, maybe completely isolated from the network. So that becomes a private network, and all these routers, all the routers on the way, will just follow that virtual circuit, follow that path, and isolate traffic. So the trick here is that you have this in label and out label, and by doing the labeling based on both source and destination, you have much more flexibility in the routing. And then the route lookups become very simple. Once you have inserted the label, you're looking at a fixed length ID. Your table is very small, so your switching becomes very fast. Yeah.
Use backbone network.
It is used in backbone networks. So a lot of ISPs use MPLS to route within the autonomous system. Yeah.
Single platform software. Yeah, they are also.
So scalable because you have an example of stable and use the graphical routing like I think the others because you have for each destination you have an link.
So again you have aggregation of destination. See, if you have only one possible outgoing path, right, you can aggregate all of them. You can aggregate a lot of different virtual circuits. So the takeaway thing from this is that this uses virtual circuit technology by inserting this header, and all processing is based only on this header. It speeds up things, and by including the source in your routing decision, it also makes it more flexible. So the complexity is in inserting this header between the network layer and the link layer. Once you're done with that, then throughout the network you get a lot of speed. So if you think that scalability is an issue, well, this label insertion is done only at the edge of the network where you may not have a lot of flows. Once the label insertion is done, then through the MPLS network you can have millions of flows, millions of packets, and it still remains scalable. Now let's switch to wireless and mobile networks. Since I started teaching this course, and since actually the book was written, wireless networks have become more and more important. Any cafe that you walk to today, or any apartment building, you open up a laptop and you'll see multiple wireless networks floating around. The number of wireless phone subscribers now exceeds wired phone subscribers, and mobility is the most important thing. Wireless technologies allow us to be mobile. And mobility is very important for consumers. And all the wireless technologies that are being developed are making mobility more and more easy. So for wireless networks, there are two challenges, which is communication over the wireless link. We saw when we are looking at different kinds of MAC protocols, communicating over a shared medium is difficult because you have to grant access to a single user at a time on a shared medium. With cables itself, it's difficult. With wireless, it becomes even more difficult. One thing that I spoke about last lecture was the hidden terminal problem. Wireless networks suffer from this hidden terminal problem. There's another problem which wireless networks have, which is an exposed terminal problem. So wireless links have additional complexities if you think about communications or communicating over wireless links over wired links. The other problem with wireless networks is how to seamlessly make them mobile. All the wireless networks, there is no single giant wireless network. The wireless network is really a collection of several smaller networks. And when a user is mobile, when a user moves from one network to another, it's the job of the wireless network to make that transition seamless. So the first programming assignment that you saw was an example of that. We were doing it on the wired network, but it really, if you think about it, it referred to this user who was switching networks, and the overlay network was handling, maintaining the identity of this user between different networks. So that problem reappears much more severely in wireless networks, where you have a mobile user which has a specific identity on the network, but which keeps moving between different smaller networks. And the wireless network has to maintain its identity and also maintain the communications that the mobile user is part of seamlessly. So there are two sort of different challenges in wireless networks as compared to wired networks. Wired networks, you won't have the mobility issue, and communication is also a lot easier in wired networks because different users can be isolated using switches or routers or other kinds of technologies. So before looking at the different kinds of technologies, well, the elements of a wireless network, through experience all of us are familiar with. You have smaller wireless networks, and all of us probably have used access points. Access points connect us to wireless networks, let's say 802.11 networks. The laptops connect to an access point, and these access points then are connected in a backbone infrastructure or a network infrastructure. So we look at details of how the system works. This backbone infrastructure could either be the internet, or if you're using cell phones, they could be the cell towers that connect to each other. Different kinds of wireless links, and there are different kinds of wireless standards. So this figure shows the different wireless standards, their capability in terms of bandwidth, and then their capability in terms of distance. The wireless networks that we are most familiar with are the 802.11 based networks. Let's say 802.11a, G, or B. They operate at the highest speed, but because they operate at these high speeds, the distance over which that they can operate is also the smallest. There are other cellular or long distance standards. If you've heard of terms like 2G or 3G, they operate at lower rates, but they can also operate at longer ranges. There's a new standard which is being proposed and which should be deployed soon called WiMAX, which lets you operate at high speeds and longer distances. So what we'll do is we'll look at the 802.11 base networks in some amount of detail. So you've heard of 802.11 networks, Wi-Fi networks. Those are the standard wireless networks that we use. Do you know the difference between A, B, and G? So A, B, and G are different standards. All of them use the same MAC protocol. The only difference between A, B, and G is in the physical layer. So the MAC protocol is identical for 802.11, but the physical layer characteristics are different. 802.11b and G operate in the same frequency range, which is roughly 2.4 gigahertz, where also wireless phones operate in. So B and G operate in the same frequency range. A operates at a much higher frequency range. The benefit of G operating in the same frequency range as B is that G is backwards compatible with B. If you have an adapter which can work with 802.11G, it can also work with 802.11B. Why? Because they are operating in the same frequency range, so the radios that are needed, the receivers and the transmitters, they are the same for B and G. 802.11a on the other hand operates in a different frequency range, so it requires different kinds of radios, receivers and transmitters. So A is incompatible with either B or G. B or G are compatible with each other because you can use the same physical device. They operate in the same frequency range, only a different modulation scheme. You've heard the term CDMA. The CDMA is another kind of MAC protocol. So what are the kinds of MAC protocols we have looked at? Let me explain CDMA today. We'll stop here and then we'll get down to the details of wireless networks. So what are the kind of MAC protocols we have looked at? Well, we looked at, okay, Aloha. So Aloha, CSMA, CD, Ethernet. All of them are random access protocols. The other kind of MAC protocol that we looked at was channel partition. And there it was TDMA, FDMA, time division multiple access, frequency division multiple access, and those kinds of protocols. Third kind was taking turns. Or polling. So a token ring, a token passing protocol, or master-slave kind of protocol which is used by Bluetooth. That's the third kind. CDMA is yet another kind of MAC protocol. CDMA stands for Code Division Multiple Access. Let me explain. The idea behind CDMA. All of you are familiar with vector algebra? You've done vectors some point in the academic life? No? Never? Yeah, that's good enough. Let's say you have two vectors that are orthogonal. Orthogonal vectors, they are 90 degrees to each other. Okay? Now if you take a dot product of these two vectors, a scalar dot product of these two vectors, what do you get? 0. So dot product what happens when you add these two vectors together? You'll get something which is in the middle. Okay? Right? You'll get a vector addition of these two together. Now, what happens when you take the dot product of this with one of these two vectors? Yeah? You get the other vector. So if you take a dot product of this, let's say with this, you'll recover this vector back. If you take a dot product of this vector with this one, you recover the scalar coefficient of this vector back. So let's say this vector, let's call this E1, E2. This vector was alpha E1 plus beta E2. If you take a dot product of this with E1, you recover alpha back, because E1 dot product E2 gives you 0. If you take a dot product of E2 with this, you get beta back. Right? You assume these are unit vectors. Now this concept is used in CDMA. So in CDMA what happens is that each user is assigned a vector. So all of us have been assigned a vector in a space, and all of these vectors are mutually orthogonal. So my vector is orthogonal to all of your vectors. Any of your vector is going to be orthogonal to any other vector. So EI dot product EJ is equal to 0, I not equal to J. Now what we are trying to do is we are trying to transmit our individual messages. Now you can think of alpha and beta as the bits that we are trying to transmit. All of us can simultaneously send the bits on this channel, and what will happen was the resultant bit or the resultant vector would be a summation of everything that has been transmitted. Okay? At the receiver knows the sender's vector. So you have well-defined pairs of sender receivers. The receiver knows what the vector of the sender is. So the receiver is going to receive this vector, which is an addition of all the vectors. So all of us tried to transmit. We came up with this signal, which is a summation of everything that everyone tried to transmit. But the receiver that wants to listen to what I sent knows what my vector is. So what it will do is it will take this vector, multiply that with the vector that I was assigned. Everything else gets washed away. Everything else becomes 0, and only what I had transmitted can be recovered directly. So that's the mathematical intuition behind CDMA. You assign codes which are orthogonal in the appropriate space. You define this inner product, and then everyone can simultaneously talk. The receiver knows what it's trying to listen to. It knows that code. It knows the vector. It will take that garbled message, perform an inner product or a dot product, and recover what the sender was trying to send. So this is an example here. You have a sender. Sender has the data bits which it's trying to send. You have a receiver which will receive those data bits. Every sender has been assigned a code. So these codes are what you think, these are the vectors. They are orthogonal vectors. So what's going to happen is these codes and the bits, instead of being 1 and 0, think of them as +1 and -1. So your code looks something like this: 1, 1, 1, -1, 1, -1, -1, -1. This is a vector in some space. Your signal, what you're going to transmit on the channel, is going to be the data bit times the code. So +1 times this, which becomes this signal. Everyone else is going to transmit similar signals like this. As the receiver will receive a summation of all the signals. So if you are trying to transmit -1, then your signal just becomes inverted. Instead of 1s and 0s, the bits are +1 and -1. It makes things easier to understand. So if you're trying to transmit -1, what you transmit becomes inverted. And what you do at the receiver end, at the receiver you know the code. So you multiply whatever you have received with the code that you already know, and what you're going to recover is the bit that the sender sent. Everything else which is part of this received signal, the signals of other users of this channel, will turn to 0 because of this property of being mutually orthogonal. And the receiver can then receive the right output, even though other senders were simultaneously transmitting. So this seems to suggest that we are getting a free lunch. All of us are simultaneously transmitting, and all of us can simultaneously listen. So if the bandwidth of, let's say, our channel is R and there are n users, has the bandwidth suddenly increased to n times R? Yeah.
All the vectors are orthogonal.
Yeah.
And that's the trouble is not figuring.
Suppose you can solve that. Well, the free lunch is not there because, you see, the length of the data bit is much longer than the individual bits of the vector. Right? In the time that you took to transmit this one bit, your code went through 8 different bits. So your code is operating at a frequency, let's say 8 times your data frequency. In this whole slot, you only transmitted one data bit. But to transmit that one data bit, you have to transmit these 8 bits of your code. So at low rates, you tend to lose out, but it's much more graceful when you have a high number of users. What you have done is, instead of transmitting at this slower rate, you end up transmitting at a faster rate. So your rate of transmission is faster, but the rate at which data is received is slower. So that this way you get around this problem of having a distributed MAC protocol, but the trade-off is that you have to transmit at a faster rate. The rate of your vector is much faster than the rate of your data. Yeah.
Won't the receiver have to have every sender's code?
The receiver has to have, so you have a code exchange mechanism. The receiver knows the sender's code.
Yeah, but if you are like M sender and doesn't know which one is sending.
No, you have to know. Otherwise it doesn't work. You have to know which receiver you're expecting from, which sender you're expecting it from. So CDMA cellular technology works like this. Every phone has its own vector or its own code. And all of the phones are using the same frequency band. But at the receiving cell tower, it can decode our individual transmissions by using the appropriate code. It knows what code the phone has. Let's stop here. We'll carry on from here the next.